Hello, welcome to NETA's virtual paper presentation, and welcome to my segment, Finley Ledbetter from Group CBS, particularly talking about vacuum interrupter conditioning today. Vacuum interrupter conditioning, what is that? It's basically a process by which we can breathe new life into an existing midlife vacuum interrupter. So let's get into this paper, and then we will answer some questions and try to go deeper into it as we can. I'm new to the virtual world. I'm an old school guy. I am a marker board and chalkboard kind of guy. So let's see if I can somehow pull this off and keep you guys for 30 to 45 minutes involved. The paper is vacuum interrupter conditioning. And I'm Finley Ledbetter. There'll be some emails and email addresses and stuff later on it where you can get a hold of me if you have any questions. And also the actual tech paper can be sent to you at some point if you want it after the presentation. There are millions of vacuum interrupters in service today across the world. This is a worldwide product, a worldwide issue. These millions of interrupters are slowly moving towards failure. What is the rate? That can be argued. If you listen to the manufacturers, it's basically never, because they're thinking that the equipment will be replaced before the vacuum interrupters fail. That really hadn't happened. This equipment went into service in the 70s and 80s, and we're now 50 years in, and we got to find a way to keep them in service 50 more years. That's 100 years. We got to find a way to keep vacuum circuit breakers in service for 100 years, and the vacuum interrupter is one of the key components of the vacuum circuit breaker. Many of these interrupters have already exceeded their life. There again, speculation, what is their life? We start to see real failure rates accelerate at about 30 years. Some of the cheaper made interrupters that are made offshore, we see even failure rates faster than that. Some of the interrupters we see seem to still be in reasonable condition after 30 years. Has to do with the manufacturing process, the materials, how well they built the materials and prepared them not to outgas. We've seen an increased number of failures. When I first got into this business, 300 or 400 years ago, we were seeing 1 or 2 failures a year, a month, a quarter. Today, we see 15 or 20 failures a day. We're essentially a funneling point for that kind of stuff because we are involved in the vacuum interrupter manufacturing, testing, and supply business as a circuit breaker parts supplier. Why is conditioning important? Because replacing them all is unfeasible. You get to a position to where your fleet is 40 years old, you're going to start to have failures. For a reliability standpoint, you'd like to replace them all, but you can't. The downtime, the cost, the labor, the potential for damage is too high. So the conditioning process is the one tool you will have to be able to keep your entire fleet healthy and to make it last longer and extend the usable life of this equipment. And that's what we all want to do. The breakdown voltage of an interrupter is shown here on Paschen's curve. The green area is a healthy vacuum pressure inside an interrupter. The yellow area is a position to where you need to start thinking about, is this a critical circuit? Is it a critical circuit breaker? Should I replace it or move it into a less critical application? The red area is a situation to where you need to act now, and you need to do something, because if your maintenance cycle is 5 years, you might get to failure before your next maintenance cycle. So you could have a piece of equipment in service that would not interrupt a fault, a severe fault, or would not do what it's supposed to do and protect your people and your equipment like it's supposed to operate. So it's real important you understand this. It's basically manufactured in the -5 PA range or lower. As its life goes along, there is a bathtub failure curve with every device, with everything, even with people. As that time approaches, they begin to fail. When they begin to fail, you need to have a plan to either to replace them, replace the switchgear, replace the breakers, or to condition the interrupters to where they will live and service properly, operate properly for many more years. And that's what this paper is about, that process. This is a study that was done of about 300 plus vacuum interrupters and similar circuit breakers that all were in service for a varying length of time. Some of these interrupters, as you can see here, and these circuit breakers were 1 to 10 years old, some 10 to 20, some 20 to 30, some 30 to 40, and you can see the failure rate of simply doing an AC withstand test for these breakers changes dramatically. You can also see that the ones that are 1 to 10 years old, we found very few failed interrupters. We found very few high pressure interrupters when using magnetron testing. When you get to 20 to 30, 30 to 40, you can see the failure rate accelerates dramatically. That's because of leaks. These aren't all leaks where pressure is coming from the outside. Some of them are virtual leaks that happen inside the interrupter when things outgas. For instance, when you see an interruption, you create heat. When you create that heat, the metal heats up, and you actually have gases that come out of the metal that contaminate and raise the pressure inside the canister to hasten failure. Breakers repetitively used, it's going to get there faster. Breakers very seldomly used, it's going to get there a little slower. There again, if the breaker was manufactured in a high quality environment, it's going to get there a little slower. The seal is going to be better because it's constantly trying to be penetrated by small molecules. So you have a lot of things going on inside these interrupters. They're all working against them. Over a period of time, the more you use them, the more high energy interruptions you see, the faster they're going to fail. That's why 5 kV contactor interrupters do not live as long as circuit breaker interrupters, because they are used repetitively. They are open and closed many times a day. And sometimes under great load with long cable links and big motors, the actual effect inside is great. So with vacuum interrupter conditioning, we're basically trying to build 2 processes. A shop process by which we can condition every interrupter that comes through ours or anybody's breaker shop or through your shop. And we're trying to build a field system where this can be applied in the field easily, where you can condition the interrupters as part of your normal maintenance program. When you typically go in and maintain a breaker, you do a standard battery of electrical tests. VI conditioning should be inserted right in that spot to where it's constantly conditioned, where the pressure is constantly kept as low as possible. And we're going to explain how that works here. This is best suited for interrupters that have little wear, have no mechanical failures, haven't been through an extreme fault, don't show any signs of wear. Now, when you get a breaker past its wear limits, no amount of conditioning will solve this problem. When a breaker gets past its wear limits, the actual wipe springs can no longer hold the interrupter closed properly, and the popping forces will cause all kinds of problems for you. So you really need to keep these interrupters in the middle of the pressure band or lower, and once you get to the wear limits, you need to replace them. There's nothing you can do about a vacuum interrupter that's seen a severe fault, that's had a thermal event, has a severe situation to where it's been repetitively used so many times, you've reached the wear limit, or the mechanical ability of the bellows and the breaker to perform. The interrupters are only rated for a certain number of operations because they see a shock every time they're opened and closed. Several hundreds or thousands of pounds of force are exerted. So they flex, 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 flex every time they're operated, and any metal can only take so many of those. What we're talking about is improving the inside pressure of the interrupter by at least 1 order of magnitude, and being able to do that multiple times over, say, a 20-year period. So if you have a mid-level interrupter that may be in the 3 PA range, which is in the middle of that chart we showed you a while ago, let's try to keep it in the 3 PA range by conditioning it every year, every 2 years, every 5 years, whatever your normal maintenance cycle is. Obviously, as the breaker gets to be a higher pressure, you'd want to condition it more often and record those ion current ratings to see if it's continuing to rise or not, because there'll be some interrupters you will not be able to keep in service. They'll be too far along the failure curve to be kept in service many more years. Basically, 1 order of magnitude that we can pretty much guarantee that we can do in a midlife interrupter will breathe at least 5 more years of useful life into an interrupter, sometimes 10, depending upon where we catch it and where we start. It needs to be caught as early as possible, because once it gets past a certain point, the ion current gets so high that our process will not have as much effect. If you look inside the interrupter, there are a lot of gas molecules, and these gas molecules are mixed inside the interrupter. And when you test the interrupter, the number of gas molecules that are between the contacts will affect the test result. You have a lot of gas molecules between the contacts, it's going to fail your AC/DC high pot vacuum integrity test. You have very few gas molecules between the contacts, it's going to pass that test. So basically they're intermixed, and there are tens of thousands, hundreds of thousands, or millions of gas molecules inside an interrupter that is very low pressure. Now what the next animation will show you is the internal materials outgas. So every time there's an event, there's a few more gas molecules that are emitted from the metals. These will continually rise in pressure and will eventually get to the point to where the breaker will no longer operate properly. The interrupter will no longer interrupt as it's supposed to. These gas molecules can be noble gases, they can be gases that are not stable, they can be some of either one. That's the number of electrons in the outer covalent shell. So what we really want to affect are the unstable gas molecules, because the noble molecules, the outside shell is already full and they're very hard or impossible to deal with. So we can never get the pressure to zero, but we can keep the pressure in a range to where it will operate correctly. What we do is we apply a high voltage, a DC high voltage. Let's just say 25 or 30,000 volts. This essentially charges all the gas molecules inside and excites them. After we've charged them and excited them, we want to do something to accelerate them. So we apply a magnetic field. The next thing we do is we approach, the next slide is a magnetic field is applied that takes this range of gas molecules that are charged and suspends them and compacts them into the magnetic field. So now we have a charged set of gas molecules that have been drawn or essentially squeezed into one area inside the interrupter. What that does is allow us to impact an acceleration when we release that field that will accelerate and move these gas molecules quickly across the interrupter. Once we release that field, this swarm of gas molecules accelerate and bounce all inside the canister. When these certain gas molecules, unstable gas molecules, strike certain metals with enough velocity or each other with enough velocity, they do one of two things. Well, one of three things. They do not accommodate and they simply bounce off and they stay free gas molecules inside the canister. We missed those. Or when they strike certain copper and stainless materials, they oxidize, they tarnish. When they do that, we've essentially taken a gas and converted it to a solid. So we have fewer gas molecules, so the internal pressure has gone down. Now, the third thing that happens is two unstable gas molecules hit each other and combine. When they do that, two have become one. So we again have lowered the pressure inside the vacuum interrupter. So we've tarnished or oxidized, converted some of the gas molecules to solids. They're no longer a gas, they're simply tarnishing the copper inside the interrupter, which does not affect the interrupter's operation in any way. This has lowered the pressure. We've combined some, that has lowered the pressure. But some have got trapped behind shields and other things, and we can't get to them. So you would have to conditioning it with pulses. So we do this in pulses, and these pulses gives us a shot to get some of those that we missed the last time. So we'll sometimes pulse this throttle, this vacuum interrupter 15, 20, 30 times in the process, as long as we're seeing advantage and gain. Therefore, it may take several minutes for this process to take place because we do it in pulses. After the VIC process, there are still free gas molecules inside the interrupter. We cannot get back to -5. We can never get back to where it was, but we continually lower the pressure every time we condition it to breathe new life. How about suck old life out of the interrupter? This VIC process, this conditioning process, we've conditioned thousands and thousands of interrupters now. We've conditioned every interrupter that's come through our VI shop, our field service people, our breakers that we sell. We condition new interrupters, used interrupters, old interrupters. We've done this and we've watched the pressures inside for many years. So we have a pretty good idea what's going to happen now. Let's move on to the final animation that shows that after the VI process is over, some of the molecules are temporarily attached to each other. Some of them are temporarily pushed out of the way. They come back and recombine. When they come back and recombine, the pressure comes back up. So you see an unusually low pressure immediately after conditioning, but there's a rebound rate where it will come back. It will come back because those gas molecules that were not combined or oxidized have been pushed out of between the contacts, and some of them have trapped behind the shield, trapped behind the bellows shield. They'll come back and accommodate in a few days or a few weeks, and the pressure will come back up a little bit. But it's not going to come back to where it was because we've destroyed enough free gas molecules that the pressure is going to be lowered between 1 and 1.5 orders of magnitude, which is going to be 5 years plus of additional service. Only a fraction of the original gas molecules will still be in the chamber after we've done this process. How many do we destroy? We don't know. The only thing we can see is ion current changing. Therefore, we know that the number of gas molecules inside have changed. And when we take the interrupters apart, we see the tarnished surfaces, we see a small brown residue, we see the things that have essentially happened inside by this process. We have a few case studies here we're going to talk about now, things that we've done in the field. We've done hundreds and actually we've done thousands of interrupters, but we're just going to highlight a few. One of them here is a set of power vac interrupters that came out of Hurricane Sandy in 2012, and we started conditioning them in 2012, 9 years ago. So we've watched them twice a year for 9 years and measured the pressure, measured the ion current, which essentially relates to pressure. And in that, we've watched these interrupters over a period of 9 years. They were also exposed to salt water. So we've been studying the effect of salt water on the stainless steel bellows and all the brazing filler material that holds the interrupter together. And that'll be another paper you'll see later on. Right now, this case study, the other one we're going to do is an ABBR mag breaker that we conditioned in 2009, and we're going to do a VCPW breaker. We're going to talk about a case study for it that was manufactured in 2011. The particular interrupters that came out of Hurricane Sandy came out of a paper plant in the New Jersey area. These interrupters were submerged in water for a short period of time, so we've done everything we could to a couple of them to slow that degradation by using processes and materials to slow that corrosion. Then a few of them we've let them just corrode to see what the delta is between ones that we treat with a particular substance that we think is going to preserve the stainless steel and the brazing filler materials and cause them not to fail. So we've seen pressures differ between the ones that we've actually processed with a chemical that we'll be talking about in a future paper. These interrupters have been tested every 6 months, so we have some particular data that's over 9 years old on them. The next slide, you see the Hurricane Sandy printout. You see it was an early VIC pilot project. We started it really in 13. It was a proof of concept for our VIC process. We still have these interrupters in our aging process. We started out with poor pulse control, which meant we were putting a sustained magnetic field on them. We didn't really have the effect that we want. We had an aha moment when we realized that by pulsing these interrupters, we could get more energy and more effects, so we've gone to a pulse model. We're also doing a saltwater contamination study on them, and we have an ongoing aging study going on these interrupters. These interrupters are still in the process. If you look to the right, you can see some of the process that we made in taking these interrupters from a certain pressure and reducing the pressure and holding it there over a 9-year period. Now let's move on to the next slide, which is our second case study. It's for a military base in Kentucky where we were called out because they had vacuum interrupters and outdoor breakers that were testing near failure, and they didn't want to have to replace them all. So we went out and did a conditioning process where we went out, conditioned the interrupters, went away for months, then come back, measured them again, and showed them the difference in pressure and the fact that the difference in pressure did live. We're going to go back every 6 months with this particular group of interrupters on these breakers and continue to monitor this process. I'm going to go to the next slide, which shows the basic reduction in pressure that we were able to achieve over the first couple of conditioning cycles. Basically an improvement from 1 order of magnitude to 2.1 orders of magnitude. There again, it depends on what type of molecules are in the canister, what condition the canister is in. There's a lot of conditions that play into what can we get. We're guaranteeing better than 1 order of magnitude in mid-level interrupters. If the interrupter pressure is very high, we will get less than that. If the interrupter pressure is very low, we'll have negligible effect. We're actually targeting the interrupters that say have 10 years of life in them, and we want to hold it there for as long as possible. For another 50 years, we want in 50 years for it still to have 10 years worth of life. That's our target. Get these circuit breakers to the 100-year mark. Based on these results, we expect further improvement on A and B phase. There again, we see one phase that the effect is different. That means that the gases inside or the manufacturing process on that interrupter was not as solid. There'll be situations, there'll be outliers, but we basically can guarantee the 1 order of improvement. We can't guarantee the 2 orders of improvement that we saw on some of the interrupters on this job. The next project that we want to talk about is one for Portland General Electric, and we've done many of these. We could talk about them forever, and give me a call. We'll talk about them. This particular Portland GE breaker was a VCPW breaker. We're not trying to hit any one manufacturer, so we're talking about ABB, we're talking about GE, we're talking about Eaton, Cutler, Hammer. There's really no distinct advantage between them from our perspective, and we're not hitting on any one manufacturer. That's why we've broken it out this way. This was manufactured in 2011. This was a generator breaker. It was a very important breaker, a very expensive breaker. The interrupter, $15,000, $20,000 for an additional pole assembly for this breaker. When you took and measured the ion currents of the 3 poles, the ion current was much higher than A and C. Even with all the insulators removed, with everything clean, with no outside factors, only current passing through the interrupter, the B phase was much higher than A and C. What does that equate to in pressure? Who cares? The ion current's higher. That signifies that the pressure is higher. No way to dispute that. We also have taken these breakers into a Faraday cage and taken and stripped out all possible RF interference. Negligible result, negligible difference in our measuring process. This VI process was performed on the breaker in 2020. We were able to get the results that we wanted. The breaker went back into service. We'll test it again, conditioning it again, both at the next maintenance cycle. The actual results are shown in the next slide, where the 3 tests were performed to give us ion current after the VIC process, and the B phase magnitude improvement was about 1 order of magnitude. That means we gave them an extra 5 years that they can push back replacing the pole assembly. Now they can schedule it, they can plan for it, they can have the parts on hand. Where when this breaker came out of a service, it was a holy shit moment to where they said, we have a problem, what can we do about it? And we were able to condition the breaker where they could put it back into service. Now they can budget for it, they can plan for it, and they know that they have a potential problem in that B phase. And in 5 years when the breaker comes out, they'll check the pressure again, and then we'll be able to determine whether we put it back into service again or do we replace that interrupter. C phase showed a greater effect. Like I said, depending upon the materials and the gases inside, we're going to see some interrupters that will show a greater than 1 order of magnitude. Basically, the synopsis was we're tracking and we'll continue to test the power vac breakers every 6 months, and we'll report back on that as time goes on. Study 2, we were called back to retest these after 6 months, and we will every 6 months, and we've seen a reliable result in the spring report, and we'll be back again sometime this summer. Case 3 will continue to condition the VI through its mechanical life and try to keep this expensive generator brake in service as long as possible for Portland GE. We need to talk about the candidates for conditioning. You can't really condition every breaker. We basically look at interrupters that have few operations. We basically look at breakers that have no mechanical sign of failure or fatigue, that have contact resistance readings that are within manufacturer specifications, that have low contact wear, and ones that their internal pressure is still far less than 1 PA. Now, in the 2 PA near failure interrupters, I think we can keep them in the 2 PA range for many, many years with this conditioning process. May we stumble onto some interrupters, for instance, ones with glass enclosures, ones that have different materials inside. Some of the other older interrupters were full of beryllium and full of gettering material that was different than what we use today. So we are going to see some situations to where we'll be able to do better or worse, but we've not seen anything we couldn't do at least 1 order of magnitude improvement. Basically, the operations we're talking about, if a breaker gets near its expected life cycle, I wouldn't condition it, I'd replace it. If the breaker's been through an extreme thermal event or has been damaged in some way, I would replace it. If the contact resistance is over 100 milliamps, or microamps, or if the contact resistance is microohms, or if the contact resistance is anyway greatly variable from the other 3, I might replace the interrupter. If the internal pressure is near failure, I would replace the breaker. You might take a swing at conditioning and see what result we get, because obviously we've not tested every interrupter in the field yet. It's a very viable process, and I think we're going to find some interrupters with high ion current that we can affect and help, but we have seen some that the effect is very negligible when you get right down close to the knee of the curve where it's about to fail. Where do we go from here? You know, VI interrupters that are near failure need to be replaced. VI interrupters that are beyond wear limits need to be replaced. Interrupters that are in the middle of their life cycle need to be kept there as long as possible. This is a thing to where we can take this fleet of interrupters, this hundreds and hundreds of millions of dollars worth of interrupters, this critical piece of the infrastructure in the United States, and extend its life. Now, we can already extend the breaker's mechanical life by reconditioning the breaker. There are tests we can do with timers measuring acceleration, speed, and velocity. There's lubrication things that we can do to improve it with improved lube, but there was not anything we could do with the vacuum breaker. With an air breaker, take the contacts apart, clean them, burnish them, put them back together, measure the speeds and contact resistance. With an oil breaker, clean the contacts, clean the oil, all those sorts of things. But with a vacuum breaker, we were looking inside a mystery. It's no longer a mystery. We can now do something to improve the life expectancy of the vacuum breaker and tag it along right with the rest of the breaker. The switchgear is solid. The bus is solid. It does not age unless corrosion gets to it or moisture gets to it. The vacuum breaker mechanism itself needs help. We have components and abilities to recondition and rebuild the mechanisms to keep these breakers in service. Now we can keep the vacuum interrupter in service without having to rush out and replace millions and millions of dollars of interrupters in a plant that, say, has 300 or 400 breakers in it. It would be cost prohibitive and the downtime would be prohibitive. I think it's important that you probably condition your entire fleet when it's brand new. It's probably as an acceptance testing standard. Addition, I think it's important that you condition the interrupters every time you have access to them. You can't damage them. Power levels are too low. You're not going to hurt them. All you're going to do is help them. Every time you can destroy or combine a gas molecule inside the interrupter, you're adding life to it. If the breaker's out of service as a spare, it's been sitting on the floor for 5 years, 10 years, 15 years without use. I myself would not put it back in service until I've done a standard battery of test, reconditioned the mechanism, lubricated, timed it, and now I would add VI conditioning to it to where you're giving it the best possible chance for it to survive in the environment it's going back into after sitting still in the corner for 5 years. Always make sure you take care of the lubrication, that particular thing. That's the number one killer. The number one killer in these breakers is not loss of vacuum pressure, it's lubrication. Never forget that. Inactivity and lubrication is your number one enemy. Moisture is number two. We have a technical paper that follows this that gives you a lot more detail. It's available to you. I've put here on the screen my email address and phone number. Jared, the other engineer that actually runs this program for me, from the hands-on perspective, his particular cell phone number and his email address. Feel free to contact Jared or myself. Jared has actually done most of the field work and done a lot of the lab work with me, and he is very versed on this, and do not hesitate to reach out to him if you can't reach me. And I can't emphasize enough how excited we are about this and what it's going to do for the industry. You know, the one thing is the equipment is portable. The lab set is more powerful, so you can do a better job in the shop than you can do in the field. You have to use more pulses in the field. It takes a little longer. You're going to add 30 minutes probably to your breaker testing program if you condition the interrupters with this equipment. I know 30 minutes times 30 breakers is a lot of time, and I realize that. I'm from the testing world. I understand that, but the benefit you get from this is great, and I don't think that you need to overlook it. Both as an acceptance testing, every new breaker, we see breakers brand new in the box where the interrupters are mid-level. We see breakers that are 30 years old that are still mid-level. It's no way to detect with the eye what you have. Measure the ion current with the ion current testing equipment that's available on the market. Compare them to each other with ion current. Condition the interrupters at every opportunity, and you will be getting the most benefit you can for your customer, client, and for the user. The conclusion, this process allows you to keep interrupters that are in the mid-range without mechanical damage in the mid-range for 100 years or longer. This process should be added to standard maintenance testing to ensure maximum life for the VIs. That's a benefit you can bring to your customer. It's something that you can do that can actually help them. This should be a normal process before putting any spares or breakers back in service that have been out of service for any length of time. We do new interrupters as well as used interrupters, new breakers in the box. I think we've had great success. We've actually not found any failures or had any failures with any interrupters we've put in the field since we've started our conditioning program at VI. We condition every interrupter. We've not had one interrupter come back at loss of vacuum since we started that process. Basically what we're trying to do is keep the installed base more stable, and we're trying to keep the installed base in service for a longer length of time. Work with us to help that happen. I know we're going to have a question and answer session here. Feel free to contact us offline as well. Request a copy of the technical paper. We also have some other papers from the past that touch on this subject. I'd be glad to forward the entire bundle to anyone that would like to have it. Please don't expect it back in the same day, but certainly a week or so after this meeting, we'll be able to process those requests and get you whatever you want. Please reach out to us by email or phone with anything we can help you with. If you'd like to be involved in our user group, if you'd like to be involved in our beta group, if you have an interesting project or an interrupter that you have a question about and you'd like for us to come help you with it, just give us a call. We'd like to come to the field. We'd like to be able to work with you and help you bring benefit to your customers and do what we can to help the industry. We're all in this together. That's it from Group CBS, from VI Inc., and from beautiful downtown Farmers Branch, Texas, where I'm at today. I look forward to your questions, and I'll try to do the best I can to keep this going as long as I can and keep doing the good work and pursuing noble causes. Thank you very much from Group CBS.